Threads are one of the most useful and effective tools in software engineering. They come with many benefits and are extremely widely used. But we can't talk about threads without mentioning processes. So let's get the big picture out of the way. Aside from the typical zeros and ones which exist in our computers, we must understand that all programs written in any higher level language, such as C, C++, Java, Python, are all compiled into binary for our computers to understand. They are then loaded into memory where the computer's operating system will allocate the necessary resources for its execution. As this program is executing, we can think of it as a process. A process is basically a program in execution with units of resource ownership. And units of resource ownership are basically the hardware that the process is using. And when the process executes, you get output. In this case, you gotta drink coffee. Now that we got the backstory out of the way, we must see where the threads fit in. A thread exists within a process. I got the animations to go with it. And it can be defined as basically a unit of execution within that process. A process can contain multiple threads, which are each executing in their own deliverables. In summary, a thread is basically a process broken up into smaller instructions. A thread comprises of four things: a thread ID, program counter, a register set, and a stack. A thread ID can be thought of as basically a unique identifier for the thread. A program counter holds the address of each instruction and tells the CPU in which order they should be carried out. A register set is basically a small set of data that holds the instructions itself, and the stack is the data structure which holds the local data of the thread. Simple stuff. Threads can have various different states. The main states for a thread are ready, running, and blocked. The ready state is basically when the thread has the necessary data has been initialized and can be computed. The running state is where the actual computation goes out, and the block state is either when the thread's done computing or the thread's waiting for some additional data. But now, when we have a multi-thread system, we have a couple of additional states, and we're transitioning in between threads. So spawn, you guessed it, we're initializing it. Blocked is either when the thread is not supposed to be running, or it's waiting for data from its coinciding threads. The unblocked state is when it can carry out the operation, and the finished state is when all the computation has been done. There are different types of thread systems. In a multi-threaded system, the different threads share both public and private resources. Threads in the same process share the same code section, data section, and operating system resources, such as open files and signals. The private resources for each thread is that they each have their own registers and stack. The reason for this is because each thread must have their own section of data to store their local computation data. Right here, we have a single-threaded system where almost all the resources are shared. But in a multi-threaded system, because each thread has its own registers and stack, having that small segment of their own local data allows for ease in computation. But why should we use threads? What's their big benefit? Well, threads come with a lot of benefits. And the main thing is time, the one resource we really can't buy. Threads minimize the context of switching time. This is extremely useful because we always want our programs to run faster. And whenever they're running faster, usually it means they're running more efficiently. And having a faster program is always a better thing. Another big thing is concurrency. Concurrency is basically parallel computation, and threads allow for that. Threads allow for parallel computation, which allows operations to carry out at the same time, which ultimately decreases computation time. They're both related. Efficient computation is because computations are happening at the same time. Threads take less time to compute than a process would. And initializing a thread is all that much faster. Another thing is that it's much more economical. It's cheaper both money and hardware resource wise because creating threads requires less resources and hardware real estate. Lastly, threads allow for utilization of the multiprocessor architecture we all love so much. This is because threads can be used to a greater scale and efficiency, and switching between threads is much faster than switching between a process. There are also different types of threads: user-level threads and kernel-level threads. User-level threads are implemented by the user, and the kernel is completely oblivious to the fact that the threads actually exist, and due to this, they're handled as if they were a single-threaded process. User-level threads are also smaller and faster than kernel-level threads. Kernel-level threads, however, they're handled by the operating system directly, and thread management is done by the kernel. The benefit of this is that if one thread is blocked, the kernel can schedule another thread in the same process. This allows us to take advantage of the multi-thread architecture better than ULTs. Both of these systems can be used in multiple different scenarios, but the kernel level thread system is the one we're most familiar with, such as Microsoft Windows, the one that we all know about. All right, now we got the explanations out of the way, let's get coding. So the programming problem that we're going to be looking at is how can we prove that threads are actually running concurrently? I'm going to open up my VirtualBox and show you through Ubuntu how we can show that threads can run simultaneously. Alrighty guys, now let's take a crack at the programming question. I got my Ubuntu VirtualBox open. I'm going to be using Microsoft Visual Studio along with the terminal. And the first thing we want to make sure is to have this type of structure set up. We want to have the int arg, char pointer argvc, and we also really want to have, we want to make sure to have pthread imported. Without this library, we really can't do any sort of computation with threads. So the first thing we're going to do is we're just going to make a thread. Just initialize it. pthread underscore t, t1. That's our first thread. It's been created. Now what we want to do is that we want to make this thread do something, anything. And in order to do that, we want to make this function. Let's just call it task right there. And we want to print f. And let's say that this is a thread. Simple stuff. This is a thread. We want to make sure that it prints out this is a thread inside of the terminal. But how do we connect this to this? So that's when thread create comes into play. So we do pthread underscore create, and we link it back to the thread, which is t1. So we use a pointer t1. Second argument are any sort of arguments that we want to put into it. There's no arguments that we want in this, so we can just put null. And next thing is that we want to connect it to the function that we have at the top. And the function that we're going to put is task. But the thing is that this takes a pointer to the function. So we want to put and over here, and we want to make this function into a pointer. Just put a star. The last thing is null because there's no return values. That's that. And now we go to pthread join. Join's a really important component of this because what pthread join teaches us is that it waits for the thread specified by the thread to terminate. And if that thread's already been terminated, then it returns immediately. Nothing really happens. So this is a crucial function for the execution of the thread. All right. So now we just go over here. We can just connect it back to t1 and null because it's not returning anything, and we're good. We can save that, go to the terminal right there. And the thing we want to be careful about is that we don't just want to have -o. We want to make sure to import the thread library as well over here, because that way this entire program knows that we're going to be using threads. Enter that. Perfect. Test. This is a thread. It executes. But now how do we actually test that there are two threads that are running at the same time? So let's make a new thread, right? If one, two threads are at the same time, make two threads. T2, two have been initialized. And now we want to basically use the exact same structure, paste that, paste that. We just want to make sure that these two things are running the exact same function, just to see what happens. And simple enough, change the variables right there, T2, T2. Run that, run that. This is a thread, this is a thread. Great. They're both running the same thing. But how do we actually know that they're running concurrently, right? Why don't we just try something else? This is the end. Whoops, I cannot spell. This is the end. Semicolons, never forget that. Let's save it, let's run it. Maybe that could change it. Oh, it didn't. Now, why is that? I mean, the thing is that the reason we can't really see if they're running concurrently is because, in a sense, all we're really doing is task and task. We don't know if they're running at the same time, if task and task are running at the same time. What we really see is this runs, then this runs. The best way to test whether they're running concurrently is that why don't we put a sleep function? Sleep of, say, 2 seconds, right? So what that teaches us is that if we have T1 running at the same time, then if T1 and T2 are running at the same time, then we'll have this is a thread, this is a thread, and then they'll both sleep for 2 seconds, and then they'll put this at the end, this at the end. So we'll be sure to have these two print at the same time if T1 and T2 are running at the same time. So we save that, go to our terminal, I guess fingers crossed. This is a thread, this is a thread, this is the end, this is the end. This proves that our two threads are running at the same time. Because if we had these two functions on top of each other without the sleep, then that's basically two normal functions. But here we have proven concurrency. And this is the best way to show that two threads can run concurrently, simultaneously, parallel, whatever you want to call it, the exact same time. And this is a great benefit for computations. I hope you guys enjoyed, and I really appreciate you guys coming here and viewing my video.